Hello my beautiful students, so welcome back to a new session with your KCET Masterstroke. So that's gonna be our third class that is related to haloalkanes and haloarenes. So yes, here in this class we are going to discuss the entire chapter, all the reaction and few reaction mechanism as well in an one shot video. So yes, without further delay, let's get started. So yes, if you are really preparing seriously for your KCET examination, don't forget to enroll yourself in your ABHYAS KCET test series launched by Deeksha Karnataka channel. So there you will get 35 mock tests and PUCs from all the chapters, so that will help you to clear your clarity and boost up your knowledge. So yes, without further delay, enroll yourself. So let's start. So here comes the content of the particular video, that what actually we are going to learn in this session. So first you can see the classification and nomenclature, nature of the CX bond, preparation of haloalkanes, preparation of haloarenes, physical properties, chemical properties, and polyhalogen compounds. So yes, so here comes the classification part. So in the classification we will discuss with respect to the number of halogen atom, sp3 nature of the CX bond, and sp2 nature of the CX bond. So whenever it comes to the matter of sp3 nature of the CX bond, we can get alkyl halide, allyl halide, and benzylic halide. And whenever sp2 carbon and X bond, then we will get vinylic halide and arylic halide. Let's see one by one. So here you can see number of halogen atom. If you are having one halogen, then it is monohaloalkane. If you are having two halogen, it is a dihaloalkane. Three halogen, trihaloalkane. If you are having arenes in your system, then again monohaloarene, dihaloarene, and trihaloarene. Okay. Now here you can see sp3 carbon and halogen bond. Here you can see this is the primary, secondary, and tertiary, like that we can break it. And allylic means one double bond, then carbon. Okay, the carbon is not directly attached to the double bond. Just after one carbon, the carbon halogen bond should be present, that is called allylic halides. Okay, and benzylic carbon, you can see benzene with one carbon, that carbon is attached with the halogen, that is called benzylic halide. Okay, now you can see vinylic halide. Vinylic halide means the carbon that is containing the double bond, the same carbon will be holding the halogen as well, so that is a vinylic carbon. Arylic means if that double bond is a part of a arene, means a benzene ring, then you can say it is an arylic halide system. I guess this is clear to you. Let's proceed. Here comes few basic haloalkanes and their common name along with their IUPAC name. Okay, so you can just simply have a look onto it. That's not that much important. So basic thing that already you know, and whatever it will come along with the questions, I will discuss it. Okay, so let's proceed. So first you can see here we are going to discuss about the nature of CX bond. So here CX bond means, whenever you are going to discuss about the CX bond, then definitely it's a polar bond. Why? Because carbon here is attached with electronegative halogen. So carbon and halogen, if you just look at the bond, this is delta negative and this is delta positive. Bond dipole moment direction is towards halogen because this is more electronegative. So as a result of this, partial negative charge is generated on the halogen atom and partial positive charge is generated on the carbon atom. Okay, so I guess it's clear to you. Let's proceed. Now we will focus on the preparation of the haloalkanes. So we can prepare from the alcohols, we can prepare from the hydrocarbons, we can prepare from the halogen exchange method as well. So from hydrocarbon we can proceed from alkanes, from alkenes. Okay, next from halogen exchange method we can use the Finkelstein reaction, Schwarz reaction. From alkenes we can do addition of HX, addition of X2. So let's do from alcohol. Okay, so here we will see, I will just show you one scheme. So here you can see I have to prepare Rx, sorry, from ROH I have to come up with Rx. Okay, so you have to see what are the reagent that I can use out there. So you can prepare RCl plus water if you just give the reagent as HCl plus ZnCl2, zinc chloride. Okay, next I can give another reagent, that is NaBr plus H2SO4. I can give NaBr plus H2SO4. That will also give you RBr, along with that NaHSO4 plus H2O, right? Next I can give, let's say, PX3. I can give PX3. PCl3 you can give. Okay, you will get 3 Rx unit, along with that H3PO3, and here X can be, here your X group can be Cl and Br. Okay, you can prepare PBr3 or PCl3 you can take. Now I am giving, let's say, PCl5. Again you will end up with the RCl compound. Along with that you will get POCl3 plus HCl. Okay, again let me give you red phosphorus in presence of X2, where X2 can be Br2 or I2. Okay, here also you can get Rx. Okay, last we can proceed with SOCl2, thionyl chloride. Here also you can get RCl plus sulfur dioxide plus HCl. So these are the method by which you can actually prepare haloalkanes from alcohols. I guess this is clear to you. So this type of so many brain maps or reaction scheme will come as we will move along with the organic chapter. So please make a proper note while you are watching the video. That will help you to boost up your knowledge in this chapter. Let's proceed. So now we will proceed how you can prepare haloalkanes from alkanes. Okay, so I can give here first I can start with the free radical halogenation. This is something you must have done in your PU1 as well. Okay, so what you have to do here, you simply have to, let's say I am having CH3, CH2, CH2, CH3. In this system I am giving, let's say, Cl2 in presence of H nu. Okay, so here I will get chlorination. Okay, but chlorination can occur in this carbon as well and in this carbon. We are having two type of carbon here, right? Now we have to decide in which carbon the chlorinated product will be major one. So let me tell you, my dear, this free radical reaction will proceed through carbon radical intermediate, so you have to check in which case the radical will be stabilized. So as you can see, for the middle carbon it is a 2 degree carbon. This particular carbon is a 2 degree one, so this is a comparatively stable one. So comparatively stable carbon will give you 2 degree radical as well, so that is the stable one, and hence the chlorine will be attached, chlorine radical will be attached over there, and that will be the major product. So CH3, CH2, CH, here let's say I am getting the chlorine and CH3. So this thing I will be getting as a major one, And another thing, if I proceed, let's say CH3, CH2, 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 Cl, that is a minor one. Okay, I guess it is clear to you. Okay, let's proceed. Okay, now from the alkenes we will proceed. First we will study the addition of HX, then we will proceed the addition of X2. Okay, first let's see. First, whenever we are just proceeding with the addition of HX, we will first proceed with the Markovnikov. So first we will proceed with the Markovnikov addition. Okay, so Markovnikov addition is something like, let's say you are having CH3, CH double bond CH2. So here it is given HBr. Okay, so in accordance to the Markovnikov addition, the bromine, means the nucleophile, will be attached to that carbon where there is less number of hydrogen. Okay, so you can see bromine can be attached to this carbon or it can be attached to this carbon as well, but in accordance to the Markovnikov rule, the bromine will be attached to the carbon where there are less number of hydrogen. So here you can see I will get this as a major product, CH3, C, here I will get Br, here CH, and here I will get one more hydrogen. So this is a major product out there. Now similarly we can proceed with the anti-Markovnikov. Okay, so whenever it comes to the matter of anti-Markovnikov, same thing I am giving CH3, CH double bond CH2. Now here also I am giving HBr, but in presence of peroxide. So whenever you are giving peroxide will proceed the reaction in the radical mechanism, and hence the major product that was there in Markovnikov, here it will be the minor one. So what will be the major product? The major product, you will get something like CH3, CH, this carbon will get the hydrogen, and the carbon that is containing more number of hydrogen, that will get the Br. Okay, so that is the anti-Markovnikov. Okay, now let's proceed with the addition of X2. Okay, whenever it comes to the matter of addition of X2, so simply you can add CH3, CH double bond CH2, and here I am going to add simple X2. Okay, so now all the double bond will be replaced by like CH3, CH, here one X, and you will get here one X. Okay, so this is the addition of X2. I guess this is clear to you. Yeah, let's proceed further. So here whenever it comes to the matter of halogen exchange, then first we will proceed with the Finkelstein reaction, and then we will proceed with the Schwarz reaction. Okay, direct name reaction they ask sometime from both the cases, so let's do it. So in Finkelstein, if you are having, let's say, Rx, okay, so here X can be either Cl or Br. Okay, now here this Rx can be treated with NaI, and the medium should be dry acetone. Okay, and the product you will get out of it, that is Ri. Whatever the X, that will be substituted with iodine. Along with that you will get NaX. So let's just take one example. Let's say I am having CH3Cl. Okay, now if I treat this thing with NaI in presence of acetone, in presence of diacetone, then I will end up with CH3I along with that NaCl. Okay, so this is the halogen exchange reaction and this is called Finkelstein reaction. Okay, now let's proceed with the Schwarz reaction. So Schwarz reaction, whatever the halogen you are having, that will be exchanged with fluorine. Okay, so let's proceed. So here you can see Rx, let's say you are having Rx, and the reagent that you can give out of it, it is, let's say, AgF you can give. Okay, you can give Ag2F2. Okay, you can give COF2, you can give SbF3. Okay, you will end up with Rf type of compound along with that AgX. One example let me write for you. So let's say I am having CH3Cl. So let's say I am treating this with AgF. So I will end up with CH3F. Along with that I will end up with AgCl. Okay, so this is the Schwarz reaction. I guess this thing is clear to you. Let's proceed further. Okay, so here we will discuss about the preparation of haloarenes. So preparation of haloarenes can be done from the hydrocarbons, from the amines as well. Okay, so from the hydrocarbons by electrophilic substitution. So let me show you some electrophilic substitution method. So here you can see, let's say I have taken CH3 along with a benzene ring. Okay, so along with that, let's add some X2. Okay, and I'm giving iron, I'm keeping it in dark condition. Okay, I will end up with ortho and para substituted toluene. Okay, so here I will get one X along with here CH3 by default. Okay, plus here I will get para halo substituted toluene. This is the para. Okay, this is the electrophilic substitution reaction. Okay, reaction with I2, these are reversible in nature. Fluoro compounds are not prepared due to the reactivity, high reactivity of fluorine. I guess this is clear. So let's proceed with the next one. We will proceed with the Sandmeyer's reaction. So in Sandmeyer's reaction, we start with the diazonium chloride. So diazonium chloride preparation, we usually start from aniline. So here let's say I'm having aniline. Okay, so let's say aniline is treated with diazotizing reagent. Let's give, aniline is treated with diazotizing reagent, that is NaNO2 plus HCl. Temperature is kept in between 0 to 5 degrees Celsius. You will end up with benzene diazonium chloride. Okay, let's proceed with the Sandmeyer's reaction. So in Sandmeyer's reaction, we usually start from the benzene diazonium chloride. So I will just show you the preparation of the benzene diazonium chloride as well from the aniline. So you can see I'm going to start with aniline. So aniline is treated with, let's say, NaNO2 plus HCl. The temperature is kept between 0 to 5 degrees Celsius, and then it will give you the benzene diazonium chloride, that is N2 plus Cl minus. Now if this benzene diazonium chloride is treated with, let's say, Cu2x2, okay, Cu2x2 Br2 Cu2 Br2, like that, then this entire N2Cl minus will released with the substitution of X, plus you will get nitrogen gas. Okay, I guess it is clear to you. Let's proceed with the same thing. If I can proceed with, let's say, Ki, let's say Ki, okay, then this N2Cl will be removed with K, with iodine substitution. Along with that, you will end up with some nitrogen gas. So this is all about the Sandmeyer's reaction. I guess this is clear to you. Let's proceed further. Here you can see the physical properties. So melting point, it increases with the mass and decreases with the branching, because the surface area itself decreases, right? Now density, the density increases with the increase in number of the carbon atoms and the halogen atom. Okay, solubility, definitely less soluble in water and more soluble in organic solvent. Solubility decreases with increase in mass because hydrophobicity increases, right? Let's proceed. Chemical reaction of haloalkanes: nucleophilic reaction, elimination reaction, and reaction with metals. Okay, so here you can see, whenever it comes to the matter of nucleophilic reaction, so these are the reaction that we are going to proceed. Different nucleophiles, then types we will study SN1 and SN2, then stereochemical aspects. Okay, next here you can see the nucleophiles. I guess you know the they loves nucleus, means they love positive, and they are electron enriched species. Okay, if these are the reagent, you can see here comes the set of reagent, and from those reagent what type of nucleophiles can be generated, you can see that. Okay, and the substituted product also you can see. Okay, so let's proceed. This is the SN2 mechanism, is very important. Like they can directly ask you, write the SN2 mechanism. So in SN2 mechanism, what happens, the nucleophile approaches from the back side, and it's a single step concerted mechanism. So it forms a penta coordinated transition state in between, and then it will give you the product. Okay, so here you will see the initial, whatever the alignment of that molecule, after addition of the nucleophile, the structure will be a little bit tilted, right? So if you start with a chiral carbon, my dear, then if you start with R, okay, then after the SN2 reaction you will end up with some S configuration. Okay, so you will face some inversion in configuration. I guess it's clear. Let's proceed in SN2 mechanism. So SN2 mechanism, these are by molecular nucleophilic substitution. Kinetics, in accordance to that, it is a second order kinetics. Steps involved, one step. Transition state, definitely, as I told you, penta coordinated transition state. In the transition state, carbon will be having 5 bonds. So carbon structure, it will be normal, like 3 carbon hydrogen bond lying in the same plane during the transition state. Okay, inversion in configuration will be shown, that is called Walden inversion. Okay, so effect of bulky groups, because backside attack is very much important for the SN2 reaction. So if you are having bulky group attached with the carbon, so backside will be hindered, right? So it will slow down the rate of SN2 reaction. So you can tell that if the carbon is 1 degree, then the rate is maximum, followed by 2 degree, then 3 degree. Yeah, let's proceed. So here comes the SN1 mechanism. Here you can see tertiary butyl bromide we are having. In the step 1 we will get the carbocation generated. So now what will happen in the step 2, carbocation will be attacked by the nucleophile, and you will get your tertiary butyl alcohol, right? So this is all about the SN1. It has 2 steps. First step we are getting the intermediate, carbocation intermediate, and hence first step is the slowest one. Okay, and Thus, it's a rate determining step as well. In the first step, only the concentration of the reactant is involved, and thus you can tell that it's a first order reaction. Okay, so these are all the information about the SN1 in a single slide. You can see it's an unimolecular nucleophilic reaction, first order kinetic it follows. It occurs in 2 steps. Solvent preference, definitely polar protic solvents. Why? Because it forms carbocation, that is a charged intermediate, right? Positively charged intermediate. So to stabilize the intermediate, you need a polar protic solvent. Okay, carbocation stability also matters. If it can form more stable carbocation, definitely the reaction will be faster. Okay, allylic and benzylic, they shows a higher reactivity. Why? Because the carbocation gets some extra stability because of the conjugation, right? Now halide reactivity, if you just look at, definitely Ri, then Rbr, then Rcl, then Rf, because I minus is the best leaving group. I guess it's clear to you. Let's proceed further. Stereochemical point of view, first optical activity, I already told you, like if you are proceeding the reaction with some optically active compound, then if you are doing SN2 reaction, then you will be having, let's say you are starting with R, you will SN1 reaction, then you will be ending up with the racemic mixture, racemization, right? Racemization means it's a mixture of R and S. So if you are starting with the optically active compound and if you are proceeding with the SN1 reaction, you will end up with the racemic mixture. But if you are doing SN2 reaction, if you are starting with R, you will end up with S. Okay, so inversion in configuration you will face. I guess this is clear to you. Let's proceed further. Okay, so here comes the elimination reaction. Here you can see the elimination takes place from the beta carbon with respect to the halogen, and the beta carbon hydrogen will be taken by some base, and that carbon hydrogen bond will jump over there and X will leave the system, and thus you will get a double bond out there. Okay, so now here you can see, for the last case, one example it's given out there. So let me just show you here. So 2 type of double bond you can get, right? 2 type of double bond you can get. One is pent 2 in, another one is pent 1 in, right? So now the thing is, why pent 2 in is more stable than that of the pent 1 in? So basically this is in accordance to the Saidzev rule. Okay, so this is basically more substituted alkene. This is basically more substituted alkene, and more substituted alkenes are more stable because of the hyperconjugation. Okay, this is in accordance to the Saidzev rule. Okay, and this is, you can see only one substitution is there, and here I am having the hydrogen along with the alkene unit. So this is less substituted alkene, and thus it is less stable. Okay, I guess this is clear to you. Let's proceed. The reaction with metal, first you can see it's an organometallic compound. It can form like Grignard reagent, and Wood's reaction, very important. If you are having, let's say, RX type of unit, RCl or something, then X will react with sodium and 2 unit of R will be attached to it. Okay, so you will get ethane out of it. Let's say you have started with methyl chloride, then if you are giving sodium, then you will end up with ethane. Okay, it's a step up process. Number of carbon will be just doubled. Okay, chemical reaction of haloarenes. So we will start, we will study nucleophilic reaction, electrophilic substitution, and reaction with metals. Okay, so nucleophilic reaction, definitely that's gonna be less reactive. Why? Because itself it is having so much electron. How further nucleophile can attack on it, right? So definitely resonance effect, difference in hybridization of carbon atom, instability of phenyl cation, because on the phenyl, on the benzene ring, if you make a cation, it's extremely unstable, it will lose its aromaticity, right? So because of these reasons, the nucleophilic attack is not that much prominent. Okay, now if you just proceed with the nucleophilic substitution, then just look at the condition. NaOH, if you are giving 623 Kelvin temperature under 300 atmosphere pressure, if you give, then you will the Cl will be replaced with OH. Okay, now what will happen if you just do some nitro group? Nitro group is electron withdrawing, right? Means the electronic density it is decreasing, right? Electron withdrawing group you are attaching in the ortho and para position. Now look at the situation, it's lesser hectic, right? 368 Kelvin only. If you give NaOH, it will be converted to Cl will be converted to OH. Now if you just look at this condition, all the nitro group, if you just ortho and para, all the position, if you just replaced with the nitro group, then if you just simply warm it, it will be changed to OH. Why? Because electron withdrawing group decreases the electron density, and hence the nucleophilic attack becomes prominent out there. Okay, I guess it's clear to you. Let's proceed further. Okay, so here comes electrophilic substitution. Electrophilic substitution can be of different type. Just let me show you one by one. So yes, okay, so let's say I am having benzene with X. Okay, so now you can see from here I can make what type of thing because of due to the electrophilic substitution. So I will give at first Cl2 FeCl3. Okay, so I will give ortho and para substituted product. Okay, so here one X, I will get ortho substituted, plus same thing I will get one para substituted, one para substitution. Okay, this is halogenation reaction. One more, let's say this is the nitration. I'm giving concentrated HNO3 mixed acid, actually HNO3 plus H2SO4. Okay, so if you give this thing again, I will get ortho and para substituted. Okay, I will get, this is the ortho substituted, plus I will get the para substituted. Okay, now what I will give, I can do sulfonation. For the sulfonation, I can simply give concentrated H2SO4. If you give concentrated H2SO4 and if you heat the system, again you will get some ortho and para substitution. Okay, so here X, here I can get SO3H, and here one more I can get the para, I can get the ortho as well, SO3H, and here X. I guess it's clear. Now what I can do, I can do the Friedel-Crafts reaction. Okay, so Friedel-Crafts reaction, what is the reagent? I can proceed with both alkylation and acylation. So first let's say CH3Cl, okay, in presence of AlCl3. Okay, so this is your, I'm just writing Friedel-Crafts FC. Okay, alkylation. Okay, so once it is Friedel-Crafts alkylation, again in the ortho and para position will be alkylated. X, here I will get the CH3, right? And again if I just proceed, I will get CH3 here as well, right? Okay, let's proceed. Now we will proceed with the Friedel-Crafts acylation. So one acyl group CH3, let's say CH3COCl, okay, in presence of again AlCl3. Okay, this is reaction is Friedel-Crafts acylation. Okay, so again you will get ortho and para substitution. So this is my COCH3. Here I will get X, and again one ortho substitution if I make X, here COCH3. So that's it. That's all about the electrophilic substitution. This many reaction you can get out of it. Okay, let's proceed. Here you can see reaction with metal. You can proceed with the Fittig reaction. Fittig reaction can give you the diphenyl. Okay, so both the benzene ring, they will be attached to give you the diphenyl, and you can proceed with one alkyl halide, one aryl halide. So Woods Fittig. Okay, so benzene with one alkyl group. Okay, so now we will proceed with the polyhalogen compound. So here you can get dichloromethane, trichloromethane, triiodomethane, tetrachloromethane, and freons. Okay, and DDT as well. So here you can see uses. First we will discuss about the dichloromethane. So it can be used as a solvent for a paint remover, as a propellant in aerosols, this type of work actually, and some manufacturers of drugs, metal cleaning, furnishing solvent. Okay, so harmful effects are also there. It can be harmful for the nervous system of the human being. It can lower, if it is taken in lower level, then slightly impaired hearing and vision you can face, and if it is taken in higher level, then you can have dizziness, nausea, tingling, okay, some numbness. Okay, direct contact in skin can face, you can face burning sensation, some redness, like that. Okay, direct contact with eyes can burn the cornea. Next we will proceed with the trichloromethane. That is also, it is a it is used as a solvent for the fats, alkaloids, iodine, and other substances. The production of freons, also trichloromethane is used. Okay, so it has some harmful effect. You can see it is, if it is taken in the lower level, dizziness, fatigue, headache, this type of things can happen, and higher level it can damage your liver, kidney, and skin. Direct contact if you are having, then intense burning, you can face mild redness, and what happens, this trichloromethane, it slowly converts to a very poisonous gas that is called phosgen. Okay, that's the reason trichloromethane is what? It is chloroform, right? So that's the reason chloroform is not kept open. Okay, it is always kept very safely in a black colored container and in a refrigerator in a dark place. Okay, why? Because chloroform, if it comes in contact with oxygen and light, it gets converted to a very, poisonous gas that is called phosgen. Okay, so to prevent this, it is kept very safely in a dark place. I guess it's clear. Let's proceed with the triiodomethane. It was used as an antiseptic, but why this was used? Because of the liberation of iodine. Okay, so tetrachloromethane, you can see it is used for the manufacture of refrigerants and propellants for aerosol cans. Harmful effects are definitely there. Lower levels, if it is taken, then definitely dizziness, headache, nausea, vomiting, and higher levels, it can lead you to the coma and unconsciousness or death. Okay, so direct skin contact can cause intense burning, and environment, yes, it has a very, very, very bad or harmful effect for the ozone layer. It causes the depletion of ozone layer. Okay, so yeah, let's proceed. This is the DDT. The chemical stability of DDT and its fast solubility is the most important or triggered problem nowadays in the society. So it is not really metabolized quickly by the animals. Instead, it gets deposited in the fatty tissues. Okay, that causes definitely ingestion. If it is ingested continuously in a steady rate, then it's built up in the animal's body slowly, right? And that can cause some harmful effect to them, even death. Okay, and that's the reason the usage of DDT is nowadays, it's banned. Okay, so yeah, that's it. That was all about the haloalkanes and haloarenes chapter. I guess you understood this. So again, in the next session it will be a PYQ session that is related to this chapter. So till then, please prepare your chapter well in detail and make a proper note out of it, and please comment me below if you have any doubt, and don't forget to like, share and subscribe. Thank you so much.